In this lecture, let's see how we can solve the recurrence relation to get the time complexity. So this is the time consumed to calculate the nth factorial by an algorithm, which is Tn, and it is equal to Tn minus 1 plus 1. So this is the recurrence relation we are having. But actually, by seeing this equation, I cannot tell the actual complexity. And I know you can't either. We need to get it in terms of big O notation. Basically, we need to solve this equation to get the time complexity in big O. So now let's go ahead and jump into learning how to solve this recurrence relation. The most common way to solve this equation is using the substitution method. In this method, you just keep replacing the values for the preceding terms up to a very few steps to know the exact pattern, and from that pattern we get a generalized equation which gets solved very easily. So let's try this. Here in this equation we need to find out the value of Tn minus 1 so that we can put it here in this equation. So let's get the value of Tn minus 1, which we can get by replacing n with n minus 1 in this equation. So when we do this, we get Tn minus 1 equals to Tn minus 1 plus 1. And this results to the equation Tn minus 1 equals to Tn minus 2 plus 1. Now again here, we are going to write the equation for Tn minus 2. That again we can get by replacing n with n minus 2 in the first equation. And when we do so, we get Tn minus 2 equals to Tn minus 3 plus 1. So these are the three equations. We don't need to find out more. Now we're going to start substituting the values. Take the equation 1 and substitute the value of Tn minus 1 from equation 2 into this equation. When we do this, we will get Tn equals to Tn minus 2 plus 1 plus 1. So 1 and 1 adds to 2, and the final equation we get is Tn equals to Tn minus 2 plus 2. Now in this equation, in the same equation, we're going to put the value of Tn minus 2 from the third equation. So after putting this value in this equation, we will get Tn equals to Tn minus 3 plus 3. Now this is a pattern. Observe this pattern. First we have Tn equals to Tn minus 1 plus 1. Then we have Tn equals to Tn minus 2 plus 2. And then we have Tn equals to Tn minus 3 plus 3. So you can write this equation in a general form like this. Tn equals to Tn minus k plus k. So here we got the equation, and now we need to reach to the base case, right? We have to calculate the time taken till we go through each element till the base case. And the base case is when we reach to n equals to 1 or n equals to 0. Take either of them in case of factorial. Here in the last equation we have taken 3 steps. And to reach the base case, we need to take n steps, right? If we take n steps, then this equation becomes Tn equals to Tn minus n plus n. So here we have replaced k with n. And now this equation becomes Tn equals to T0 plus n. Always remember, you want to get this equation in terms of T0. You can see this equation, it is having the term T0. Once you get this term T0, you can remove it, and now you're only left with Tn equals to n. And you can simply wrap it with O. That's it. This is the time complexity of the algorithm to calculate n factorial. Now here, if you go with the base case n equals to 1, then from here you have to take n minus 1 steps to reach to n equals to 1. That is to the base case, right? So here we will replace k with n minus 1. Or you can simply put n minus k equals to 1, as you want to get the T1 term this time. So this results to Tn equals to T1 plus n. So this is what we wanted. We wanted to get T1 in this equation because T1 is the time consumed by the base case. Base case is n equals to 1, and As we're not calculating anything for the base case, the value is already there, we're not calculating anything. That's why we ignore this term t1. And finally, we're left with Tn equals to n minus 1. N is much larger than minus 1. Again, ignoring minus 1, we get the complexity On. So this is how we calculate the time complexity, or we solve this recurrence relation. Let's take another example. Again, the one that we talked about few minutes ago. Let's write the recurrence relation for getting the nth Fibonacci number and then solve this relation. So the general recurrence relation is Fn equals to Fn minus 1 plus Fn minus 2. Now let's write it in terms of t. So replace Fn with Tn, Fn minus 1 with Tn minus 1, and Fn minus 2 with Tn minus 1 minus 2, and 1 unit to add both the values. And now we're going to start solving this equation, and to make it a little easier, we're going to make an approximation here. It is that time to calculate Tn minus 1 is almost equal to the time taken to calculate Tn minus 2. So if we take this approximation, then we can replace Tn minus 1 with Tn minus 2 in this equation. So we get Tn equals to 2Tn minus 2 plus 1. But precisely the time taken to calculate Tn minus 1 is slightly greater than Tn minus 2, right? So we say that here we are calculating the lower bound of Tn. So this is the first equation. Now let's get the equation for Tn minus 2 so that we can substitute it in the equation 1. So Tn minus 2 we can get by replacing n with n minus 2 in the first equation. So it is Tn minus 2 equals to 2Tn minus 4 plus 1. And now the equation for Tn minus 4. Tn minus 4 equals to 2Tn minus 6 plus 1. Now let's substitute the value of Tn minus 2 into the first equation. When we substitute the value of Tn minus 2 in the first equation, we get Tn equals to 2 multiplied by 2Tn minus 4 plus 1 plus 1. So this becomes Tn equals to 4Tn minus 4 plus 2. And now we're going to put the value of Tn minus 4 from the third equation into this equation. So let's put the value. When we put this value in this equation, we get Tn equals to 4 multiplied by 2 Tn minus 6 plus 1 plus 2. This becomes Tn equals to 8 Tn minus 6 plus 3. Now see the pattern. The first equation was Tn equals to 2 Tn minus 2 plus 1, and then we have Tn equals to 4 Tn minus 4 plus 2, and then Tn equals to 8 Tn minus 6 plus 3. So see the pattern. Let's write it in a generalized form. Here 2, 4, 8, we have them in powers of 2, right? The respective values are 1, 2, 3. 2 raised to power 1, 2 raised to power 2, 2 raised to power 3. And there can be a relation of these powers 1, 2, 3 with these values getting subtracted here. So here we have n minus 2, n minus 4, n minus 6. So this we can write these values as n minus 2 multiplied by 1, and then 2 multiplied by 2, and then 2 multiplied by 3, right? And this value getting added at the last, 1, 2, 3, these are also the same. So the relation we get is Tn equals to 2 raised to power k T n minus 2k plus k, right? Now we have to get this equation in terms of T0 because n equals to 0 is a base case. So to get the term T0 in this equation, what is needed? For that, the value of n minus 2k must be 0. which gives us n equals to 2k, right? And from here we get k equals to n divided by 2. Now let's put this value in the equation. When we put this value in the equation, we get 2 raised to power n divided by 2 t n minus n plus n divided by 2. So here we get the t0 term, which we can ignore, and 2 raised to power n divided by 2 is much larger than n divided by 2, so we can ignore n divided by 2. And finally we get tn equals to 2 raised to power n divided by 2. Let's wrap it in O, and this is how we get the complexity. This is the lower bound for the time taken to get the nth Fibonacci number, as we took approximation considering the lower bound n minus 2. We can also calculate it using the upper bound when we replace tn minus 2 with tn minus 1. I want you to try that on your own. So the complexity that you'll get in that case will be 2 raised to power n. Hope you understood these patterns, that how we solve the recurrence relations. So this was all for this lecture.